All right, so we pretty much finished everything in the course. We're just looking at reviewing today. Tuesday, we're looking at the end of the test. It should be opening up soon. And we can also use that day for anything, any questions you got. So it'll just be another review day. So I mean, really all we got the rest of the semester is just review, because after Thanksgiving, we got exam review. Now, just in case you missed it, final exam for this class is Wednesday, December the 8th from 3:30 to, I'm sorry, no, that's not June. It's 11:30. So 10:30, no, 3:30 to 5:30. I did it right. That's right. Yeah, 3:30 to 5:30 p.m. Remember, this is a face-to-face class. So I would encourage you, to start coming back to get used to this, because the administration is pushing us to do this, as a face-to-face class. So, I mean, I've been trying to be lenient on that because of the fact that, COVID and all that. Plus, I mean, I don't mind the virtual, I like the virtual aspect. And I try to cater to students that are doing, so that it's viewable by people here and virtual students. But like I said, the way this class is coded is it's a face-to-face class. So that's why we're testing like that. All right. Anybody got any questions?
No.
Hello?
Yes, anybody got any questions?
Hello?
Yes? But it's so Dewan out in the hall. I thought he was coming. All right, so what I like to do, I mean, like I said, just go through these. I really want to get y'all's brains working on these. I mean, I, for the most part, could work these kind of problems if was me being tested. But I want to get you guys blood stirring so you can figure out how to do these and test type problems. So on this first one, they give us this example of a person who sells a house in 1884 for $26. And then she puts it into a bank account paying 4% interest. How much would the investment be worth in the year 2009 if the interest is computed in the following way? All right, there's two different ones, monthly and continuously. All right, monthly essentially means 12 periods out of the year, okay? So what would we do to do A? How would we handle this? We know certain things. We know P is equal to 26, right?
Yes.
All right. And we've got R is equal to 0.04. For these kind of formulas, we really need to have the percent written as a decimal.
Over 12.
Right, and it's 12 because it's monthly. Now, the T, we might have to do a little bit of figuring out because the T see, it starts in year 1884, so 2009 minus 1884 means that we're looking at the 125th year from 1889. So we're going to put 4 times 125. Okay, and that's years, but it all kind of gets taken care of in the process. So we're going to just fill this in and see what we get. All right. You use F there. I thought in the past we used A, but okay, so look at the way I got it set up and see if you see any issues with it, all right?
No issues.
Okay, so I got everything in here, so I'm just gonna have to kind of do a little bit of simplification first. I'm gonna do the inside. So it's 0.04 divided by 12. So that's 0.003333, and then I'm going to add 1 to it. So it's 1.00, and then it's a repeating decimal. And then the exponent is going to be 12 times 125. So that's going to be 1,500. Really, oops, this is 26. 2. All right, so I'm gonna do this again. So I got all of those decimal places to be more accurate like that. All right, I'm gonna raise that to the where is it? To the 1,500 power. So we got 147. I'm just going to go out to 1.8, and then we're multiplying that times 26. So this would be 3,000. It looks rather low. I want to go back and check. Oh, I bet you I know why. I remember doing one like this, and it was it came better, but it was twice the interest, so that's probably why. So $3,826.79. Let me just double check this because I don't know. It's okay.
Redo that part again with when you raised it to the 1,500 power on there.
Yeah, let me do that. may have messed up because it seems awful low. All right. So one, I'll tell you what, I want to get that accuracy in there, so we'll do that. All right, plus one. So raising that to the 1500. 147.18. Times 26. I mean, I guess I said, I thought I did one earlier and it came out. But like I said, it's probably the interest rate. I'll tell you what, I'm gonna go and use the calculator over here just to make sure. All right, because this also was a calculator. Let's see, it's
0.04.
I gotta put it in. I don't know if I can do it in. Okay.
0.03.
How many decimals is point two? Yeah, 2 decimal places. Okay. You're right. Like I said, this, you would think that it being around longer. Okay, you know what, too, is the one that I had looked at previously. It was actually even earlier than this, so this is 1884, so I guess that's right. Plus that one had like 8 or 10% or something. All right, so the other one, we gotta use compounding continuously. So we gotta use that formula. Let's see if I got enough room here. Do that. Usually this one's a little bit easier. All right, so the same values, except that we just don't need the n. Okay. And the thing about this, we should be able to check it against that one. So as long as it's a similar value, then that's going to give us what we need to. All right, so it was 0.04 times 125. All right, so let's say, let's use the calculator. Always take advantage of these kind of things. And if you use them, when most of them have that memory thing that you can do this with. So I would do the power first. So that ends up just being 5. 0.04 times 125. 125. Okay, so 5. 26. Right. And I think I found that E key on here, at least when I was in the office and doing it. But I don't see it on here. There was one that said E to the X. Because this is just E, but there was one that had E to the X. Why don't I see it? On here. I can see it. I used it this morning in one of the classes. I mean, the only thing you think is that each calculator is version or something. All right, well, we'll just use the
What is F through E on your calculator at the top?
This one?
No, if you go all the way up, they got D, E, G, then F through E. What is that? No, go up, right there. What is that?
Oh, that's going over the degrees. Generally, a scientific calculator defaults to radians. So that's for trigonometry. So usually what you have to do is you have to switch over to degrees.
Oh,
That's what that is.
and the F through E? Oh,
I'm not sure what that is. It might be, I don't know, it might be a conversion between, I don't really know.
okay.
Anyway, let's look at this other one. The Desmos should be able to do it. Okay, so E. So 148. What about that? Big surprise, right? So 148.41. So very similar. So that's one of the good things about this one is you get to do it both ways, and there'll be some difference, but it's tell you whether you were in the ballpark. That's strange about that E, because it's in there on that calculator in my office. All right, so 148. So again, oh, you know what? Okay, what it is, that's exponential notation. In other words, I've had students would come to me with calculators and say, oh, why is it coming in this form? And after it gets, especially on just on a calculator we use for Math 203, which is like the graphing calculator. After the number gets a certain amount of zeros behind it, it automatically writes it in decimal notation. And so students get confused about that. So anyway, 3858. .66. All right. So both pretty close to the same thing. So sounds good. I'm not going to put them in there. All right. So just about the graphing. Now, remember, the graph of the exponent starts over here, gets higher. All of them, no matter what the base is, they go through 0, 1, 0, 1. In other words, when x is 0, then this whole thing becomes 1. So it goes right there. So that's the point that I would say use to make your transformation with. In other words, this +2 means that that's going to affect on the horizontal axis movement. And it works just the opposite of what the sign is there. So because essentially it's based upon x minus a minus. So when you have x +2, that means x minus the -2. So that means what's going to happen is vertical transit horizontal. So I need to go over 2. So in other words, when x is equal to -2 + 2, that gives you the 0. So now from here back to here was that shift of 2 to the left. All right, does that make sense?
Can you redo that again? Because I had problems with graphing it because they want you to do the asymptote, or however you pronounce that, and that, and I kept getting it wrong, so I didn't know how to graph it on
All
that.
right. So this is the basic graph of an exponent. Looks like this, okay? It starts down here real close to the x-axis, it gets higher, and they all go through, the basic ones, through that point right there, 0, 1. Okay? Because anytime you have a 0 exponent, then the value of the exponential expression is 1. Okay? Because anything to the 0 power is 1. All right. So this right here, there's not a whole lot to do. Where's the, okay, here we go. So now you got this thing right here, tells you vertical or horizontal. We want horizontal, and we want 2, 1, 2 to the left. Okay? Does that make sense?
Yes, but then they ask you, and it's asymptote, so the other one
Okay.
has to be in a dash form. Yeah, asymptote. So the other one have to be in a dash form.
Okay, so the asymptote is x is equal to, I'm sorry, okay. So x-axis, so y is equal to 0. All right, because this is y is equal to 0 right here, the x-axis. So see how it's going to get closer and closer, but yet never get there. So that's your asymptote. This right here is just going to keep getting higher and higher. There's not going to be any asymptote on this side.
Right, but how do you graph it? Because they want you to grab both. And I couldn't do that one on that.
Oh, okay, all right, all right.
Yeah, they was asking you to grab both of them, and I kept getting the graphing wrong because I didn't know how to do
All right.
the other one.
Here, see this right down here?
Uh-huh.
Dotted line. So, no, that's not the one I want. I mean, that's what I want, but I don't want. So what I want is I want to put another line.
Right.
So I'm going to use the line tool. Wait a second. Let me do the second one. Okay. All right, so let's do this. Let's try to do the line. All right, and then make it dotted. So there's your asymptote. Okay. So I'm unselecting now. So there's my asymptote. I unselected, and then I'm going to do this one. And as I said, yes, then I'm going to shift to, and we got it. So you see that, Tamika?
Yes, I see it now. I just had a hard time trying to, and I'm like, oh my God. All
Well,
right.
probably, I mean, the way I did it, I did the asymptote first.
Mm-hmm.
Probably doesn't matter. Then made it dotted. Then make sure I was not selecting anything. Because otherwise, if you got the line selected, then it's going to want to. Lance?
How do you know that?
Because you can see it. See how it's getting closer and closer and closer here?
No, before you graph it, how do you know?
Generally speaking, because there's no shift on the exponent y-wise, then the basic exponent is always going to be y is equal to 0. Now, if we were to do a vertical shift, and I think that's what's going to happen in the next one, that asymptote can change up and down. I think in the next one, you'll see what I'm talking about. Okay, so the domain is And then the range is going to be 0 to infinity. All right, y'all see that? Because it's never, ever, ever, never going to get down to 0 on the y, below the 0 on the y. So that's why it stops at y, and it's got a parenthesis because that's the asymptote. It's never going to get there. And on the other side, it's just going to get higher and higher. Now, on the domain, the first one, it's essentially, you could put in negative, I'm sorry, you could put in negative 500, or you could put in 500 as an exponent. There's no restriction on that domain. All right, so this one now has got a vertical shift. Vertical shift. All right, so this is going to mean that it comes down here. And I'm going to put that asymptote. So in other words, what is, since before on this last one, see, there was no plus or minus on the whole function. So that's why it was 0, because that's the basic function, has asymptote 0. Y equals 0. But this one is just going to move it down there. So I'm going to put that one in first. And there. All right, now. And then I'm going to bring it down vertically. And you see that? There's your asymptote. So the asymptote, if there's nothing added and subtracted to the function itself, then it's going to be 0. Y is equal to 0. Hmm?
You see how like this, the first is coming from -3 to like
Bring that down. All right, let's finish answering this, and then I'll just show you some stuff. Go back. So the domain is going to be again.
The asymptote first.
Oh, it's I'm sorry. Y is equal to -5. So then here, negative infinity, comma infinity, and then here is -5.
So the -5 is not included?
No, because that's the asymptote. See? Remember, the asymptote for the asymptote, that means it's getting closer and closer and closer. It never gets there. That's going to make it essentially undefined at that point. So it never gets to that. All right. See, it's getting closer and closer, but you can't, it's hard to see that on a graph. Let me see if I can do some stuff over here. What's the next one? All right, so let me just do some graph fooling around over here. Because Lance had a question. Okay, let's say we got 3 to the x. Okay, so see, if you like zoom in, see, it's never going to get there. It's getting very close, but it's never quite there. And like I said, you click on a point, see how it's y is 0.00000003. Well, it's just going to get smaller and smaller and smaller and smaller. There's an old joke about how this works. Like the difference, this is an old joke about the difference between an engineer and a scientist. And I don't know, I probably shouldn't tell this joke. I'm going to erase that joke because now it's probably not a good thing to say. Another thing about it. But basically what it is the gist of it is, let's say you have somebody in a gymnasium And every time they move, they can move half the distance to the other goalpost on a gymnasium. So in the first move, they're at half court. Then they would go half again, they're at quarter court. They move half again. They get closer and closer to the basket. But what's going to happen if they only go half? Now, when you get smaller and smaller or closer and closer, you don't ever get there. Now, the distance may be inconsequential, because as I said here, if you were to go back over here and see, if we go way, way out here, and we click on this, it's not, I mean, they even rate it as 0 because it rounds to 0, but it's never actually there. It's probably 0.00000001 or something. Let's just see if we zoom in. But it never gets there. That's why it's an asymptote. It's never going to get to that. It will never touch that. And evidently this is not always the case. I'm not sure of that. But anyway, we're going to show now, let's say all right, so when we add to the function itself, see, it pushes it up 4 on the vertical. The asymptote then becomes 4. Because now that's where it's going to go. We'll never get there. Let's just do the same thing. All right, say, oops, the X. Down. And then when we fiddle inside, and with these, the asymptote will always be that x-axis. The y is equal to 0 if we do it on the inside. As I said, 3. All right, see, that doesn't affect the asymptote. It's only the one that's added and subtracted to the basic basic exponential function. When you do it inside of the function itself, in other words, when you do it to x, it doesn't change it up and down. Therefore, it doesn't affect the asymptote. But on the other way, it does. So it shifted over back and forth, but it's still headed towards 0 like the original. Like this. All right, let's see. All right, so how can we evaluate this? All right, this is log. What we're going to do is I would just write it as an exponential form. So this is base 81 for the exponent. And it's raised to what power will give you 9. All right. Well, x has to be 1/2. So 81 to the 1/2, which means, by the way, the square root of 81. So in this case, it has to be 1/2. Might even be able to do that. Probably could also do that as an equation. Let me try something off the cuff here. Make them both. So then that's 9 to the 2x. 9 to the 1. So same basis, so we can just write it as equation. And you get the same thing. So if you didn't recognize it by putting it in the exponent form, you can essentially give them the same base in this case and figure out this one half that way too. All right, questions about that one?
No.
All right, so, oh, and I was going to show one more thing to kind of, that Lance asked about. He was asking about the negative. Okay. See that? It's a mirror image across the y-axis by negating the function itself. And then if you were to, and then this is going to give you the mirror image across the other axis. That. So inside the function has to do with the y-axis symmetry. The x-axis symmetry deals with when your function, you're changing the function sign. All right. So the basic exponential function looks like the green one here, here, and here. All right, they've got, this one's not, that's the one where if it was -4 to the x power. So it's one of these, and then the log, remember, is the mirror image, okay? Remember, it's just the opposite. In other words, the x's and the y's get turned around. So let's just look at this one. I don't want to just get real big on it. And what I'll do is I'll go ahead and show you. This is it, but I was going to. That was 4, wasn't it? All right, so let me just show you. When you got the log of the exponential function, like I said, they're inverses of one another. So notice that instead of going through 0, 1, like all exponential functions go through, that the log goes through 1, 0. And if you look at another point, 1, 4, well, this one goes through 4, 1. This one, none of the other ones go through an exact point. This is almost -1, 1, but the corresponding one is over here. So it's symmetric to the, this line. Okay, it's a mirror image of what across y is equal to x. So this is the one. Any questions about that? I mean, this right here is just a downward shift, like 4x, 4 to the x minus 10. This one right here, that's the negative x, and it's shifted down one. So this is the only one. And this one right here, the log is the same. Now, these are still mirror images. And if I'm not mistaken on this one, what this one is, it's like fourth, what is it, like a fraction? In other words, 3/4 to the x. That's the one that flips it across like that. Actually, no, this is just the -4x right there. And so this would be the negative log x. Anyway, but that's the only one. Remember, the basic log exponential function has that same shape for all of them. They all go through 0, 1. And so the log of the same base is going to be mirror image across x. Y is equal to x. All right. So begin by graphing y is equal to log 3 of x. Then use the transform information of this graph to graph the given function. All right. So remember, that's the one that looks sort of like this. So the first thing that it does is there's really only one shift, and it's the shift inside back and forth across this. It's going to be -7. So okay, so that's the original one right there. That's the log of 3x. So let's do another one. I'm going to shift it. I thought I wanted both of them. So now what this is, it's a back and forth shift. So it's horizontal shift -7. All right, because it's inside of the function. So this is 7 units to the left. The asymptote is now x is equal to -7. So now here it was 0. The domain is going to be limited now. It's -7 that it never gets to and going to infinity. This is the one occurrence where the domain has restrictions on it for a function, because the logarithm is a function, and then the range is just the negative infinity. Okay, questions about that one?
No.
So the only thing it had, and that's one of the things I've noticed on these kind of graphing things, when we were looking at graphing for functions back in whatever chapter it was 2, that would have been the end of 1, they would do several of them at once. But with these, it's just usually one shift, either up or down. They may do a reflection. I have not seen any reflections. I've gone through these a good bit. So mainly I've seen the shifts either vertically or horizontally. And this is a horizontal shift to the left. All right, same thing. So remember the log of x. It's just that. And so what the negative x is going to do, I don't know if they let me put 2 in here, but I don't think they will. So what's going to happen is it's going to go 4 to the right. Because it's inside the function, it's the input that affects x. You know, if it would have been log of x, close parentheses, plus 4, then that's an up and down, one up. And if it was a negative, we go down. So the asymptote then is x is equal to 4. And then the domain is going to be, well, you got it, see. Now it's got both of them. Anyway, the domain is restricted now for this. It's never going to quite get to 4. Because what happens is, if you put 4 in there, you get 0. That's the least value you can have. All right, so then going all the way to infinity. And the range, well, that's the negative infinity to infinity. All right, so for this, they're just saying use either common or natural logs to do this evaluation, because it's an uncommon logarithm, and as I think I may have told you, I don't know that calculators have any way to evaluate other bases, okay, than 10 and nat and e. So what we're going to do, we're going to use this, and then the one in the numerator is going to be the input. And it doesn't matter which one you use. You can use the natural log or the common log. I'm going to be different. They did the common log. I'm going to do the natural log. But you know what? It doesn't really matter. They're both going to come out the same, because it's the relationship between the two that determines this. Right, so put it there, and then 89.5 ln. So that's 1.66. And that's an approximation. Okay, use properties of logarithms. So remember, there's the product rule, and then there's the quotient rule, and there's the power rule. So this one is just a matter of using the quotient rule, because we've got so this would be put into one log. The numerator is going to be the first one. And then down here is the number. Yeah, they may be parentheses. So you may need to do this in order to get it to work. So this is probably what you need to do. Just to make sure. Functionally, it would be the same whether you have the parentheses or not, but that makes sure that we know that the input is that rational expression. All right, so property of a logarithm. So we got a power rule thing, and then we got an and, which means product. All right, so the 6 comes out in front, so this is equal to log y plus log z 6. And then the product rule is multiplying them into 1. log of y z 6. Okay, questions?
No.
All right. Those properties kind of tend to stick with you, or at least with me, the easiest. All right, so solve the exponential equation. We kind of did that on one already, but we didn't really need to, but let's go ahead. Because I showed you, you could solve that, put that initial problem. And what was it? How it said evaluate without using the calculator. And like I said, you could do it as an equation because they had a base of 9 and 81. And you write the 9 as 81 squared. And then that x was in the exponent, and then you just set the 2 equals 1. The variables each, because once you got them written the same base. All right. So first step is, if this can't be written as a base 3, then we're going to have to take another approach. You know, natural logarithm, but this one can. So once they're the same base. That's, okay, and then you can check it and see.
The solution set would just be 2, correct?
That's all it is. Because all they're essentially asking is, you know, what are you going to put there for that x in order to get 9? So it needs to be squared. So this is the same thing. Let's see, we're going to get 20. I'm just trying to figure out how far to go. Because we still got,
Would you be able to continue the rest of it on Tuesday?
yeah,
Like we stopped.
let me just do this one more, and that'll be a good breakoff point.
Okay.
And then we'll do the rest of it. There's 8 more. And we can do it because, all right, so this is. All right, so this is 81 x. Now, this right here can be written as 3 to the negative 1/2, correct? There's 2 things at play there. Remember, 3 to the 1/2 means square root of 3. 3 to the negative 1 is 1 over 3. So when we put those 2 together, that's how we get what they have there on the right side. It's a negative 1/2 because it's both the reciprocal, the negative, and it's a square root. All right, now this one has to be written in terms of 3 if we need to do this. So so this is 3 to the 4th power, isn't it?
Yes.
81.
Yes.
And then it's the negative 1/2 of that. So now, won't use the power rule, 4x. So 4x is equal to negative 1/2. And then this is one of those, when I go through Math 09, 7, students are pretty inured in thinking about solving for X, that you divide by that number in front. And this is the order that we run into problems thinking about that, because remember, division is multiplication by the reciprocal. So if we have 4 and we divide by 4, that's 1. But it's the same thing as we take 4, which is 4 over 1, times 1/4, and you get the same thing. So instead of dividing by 4, I'm going to multiply both sides by 1/4, because that's going to make the right side easier. All right. So this is still X is equal to negative 1/8. All right. Negative 1/8. Meaning that, that the 8th root of 81 as a negative is going to be 3. All right. So any questions? Like I said, yes, just make sure. Let's see what I have. I got 24. And we can talk about it on Tuesday. If you want to go through Wednesday, I'd be willing to do that. Just realize you're on your own, because I'm not going to be waiting around on Wednesday night. All right. I'm not going to have my class on Wednesday because we're all caught up in that class. So that optional is optional, and I'm opting out on Wednesday. All right. So if you want that, you can let me know. But please choose with caution, because like I said, you got no teacher around. Well, that's happened before. It's just I'm not usually around at midnight anyway. But. Sure. All right. So if anybody's got any questions, stick around.
No, thank you so much.
Okay.
I'll see you Tuesday.
All right.
Have a good weekend.
I have one question.
Mhm. Technically, you're not supposed to be using that calculator, but what do you want to know?
I'm not.
No, technically, you're supposed to be using the TI. This one, much cheaper calculator. Where did you get that at? Did you use that in school?
Yeah.
It's in here. It's TI. What did you want to know about it? I mean, I'll show you, but technically, just realize you're supposed to be using that. It's the same one we use. Technically, you're supposed to be using this. But I'll show you what I mean. Search. Probably the other one too, and it's. I don't usually deal with it there, deal with it this late in the semester, So that's technically one you want to use, but
Well, is there any way to, when the problem is like log B15 to the 84th or something like that, is there any way to do
I don't think so. I mean, that's what I'm saying is, that thing's got so many learn functions buried in there. I don't know. See, there's got the 2 prominent logs there. So,
it? So I could do it as like log to the 84th.
Well, that's why we had- yeah,
Yeah.
yeah, that's the way that I'm showing you to do it, because we're going under the assumption that you can't do an odd base like 15 or 8 or 7. that the calculator is only gonna do natural log and log. There may be in there, but I mean, I would know where to do it. I know a little bit about using that with statistics, but that's about it. Technically, you're not supposed to use it here. So, but this is the one we're supposed to use. All right. All right, Sydney, can you hear me?